The chairman for this session on detectors technique for cosmology and astroparticle physics. I will co-chair this together with Regina Caputo. She's from Goddard. She's here. You want to? No. She will present the posters later on, so you will know her. Okay, the first speaker is Nicholas Solomé. He will talk about developing of a neutrino detector for space flight.
All right, thank you for inviting me. Today's talk is in cooperation with Marshall Space Flight Center, Jet Propulsion Lab, South Dakota State University, University of Minnesota, and a team of other faculty and students here at my home institute, the Wichita State University, although NASA pays my summer. The background here is that experimental particle physicists have started since about the 1990s to do a lot of new things with NASA. They could take something simple like a spark chamber and they could put it someplace into space like where NASA or PIsa could send it and do some very unique science. As a graduate student, I was working at CERN and I come out of the group of George Sharpak and he was my thesis advisor. And one day in 1992, he walks into the office and says, "What's NASA doing? They're launching a spark chamber into space and we haven't used spark chambers in particle physics since the 1970s. But this was the GRET Gamma telescope. It was a stack of spark chambers. It ran for a long time, but it was able to put something into outside the Earth's atmosphere, and they could see for the first time high energy gamma rays, and they could do the first map of the universe in high energy gamma rays. So something similar to that has come up in the suggestion I made to NASA's Innovative Advanced Concept Office, and that is, what can we do if we operate a neutrino detector in space? What kind of new science could be done? On Earth, we could collect a few hundred solar neutrino events, but from the sun. And the 1/r² relationship means that if you go closer to the sun, you could increase the luminosity of neutrinos by 45,000 times. Now, that's pretty far into the future, but right now, where the Solar Probe Plus spacecraft is going every 90 days, the neutrino flux is at 7 solar radii is actually increased by a factor of 1,000. And NASA wants to eventually go to 3 solar radii where it would be 10,000 times the flux. So this is a counter concept to what's been going on in solar neutrino physics for the last 20, 25 years, make the detectors bigger and bury them deep underground. Well, there's another way to approach this, and that is go closer to the source. And a 25 kilogram detector would be like 25 tons here on Earth, or a quarter of a kiloton if you were at 3 solar radii. So there could be some great advantages, but you have to figure out how to operate a detector in space. Also at the same time, dark matter searches, if you go away from the sun, you would reduce your solar neutrino backgrounds by 10 times at the asteroid belt, 100 times by a moon of Saturn, or 1,000 times less at a moon of Neptune. So neutrino detection techniques, the original one for home stake was to have the electron neutrino interact off of chlorine-37, and you look for the amount of argon that's in your cleaning fluid solution, and this is how Ray Davis did it. But the technique we're going to use is going to be, that I'm proposing, we use a little different. It actually is very similar in a lot of ways to the way in which Cohen and Reines observed the antineutrino for the first time in 1954. They took an antineutrino, hit it onto a hydrogen, saw the positron emission annihilate with the atomic shell electrons, and then they thermalized the neutron that was emitted and had a secondary delayed pulse. But that was antineutrinos. Solar neutrinos are neutrinos, but we have a technique. We could take gallium-69 or 71, have it interact with the neutrino, see a prompt electron. 66% of the times you produce germanium in an excited state, M1 or M2, nuclear excited state, which has a fixed half-life of 5 microseconds or 2.8 microseconds, and a well-known energy X-ray, gamma ray emitted. And so we just need a detector that has a lot of gallium. And we've chosen for our test flight, and this is the actual GAGG crystal with its 4 components that's going to fly in space, because we've already ordered the detector sensor head and we're currently building at Marshall the Avito ray, and the shielding is being built at Wichita State with my group. And so the electron neutrino comes in, produces that conversion electron that 66% of the time the germanium, and you emit the gamma. So lab tests are underway for this detector that's going to fly in space at Wichita State University. We've been looking at energy resolution, linearity, and signal shape. We have two different types of sources here on the GAG crystal. The sodium-22 producing a nice 511 line with, you can see fairly good energy resolution there. The strontium source, which actually has an electron that's very similar to the electron that would be emitted in the conversion electron of neutrino. And then there's the yttrium-90, which you can't remove from the, which is a daughter product of the strontium, which also then beta decays, but it has a higher energy. So we've been looking at the strontium sources to tell us what the signal would look like when we have the conversion electron, and we've been looking at the various gamma rays to make sure we can understand what the secondary delayed pulse would look like. And that's the way we would clean up our signal. So instead of building the detector bigger and going deeper underground, we're taking a small detector, putting it close to the sun, but we need to find a way to clean up the signal, and our clean up the signal is a delayed double coincidence. The gamma sources, we did some studies with cobalt-57, so you could see the 122 keV line with the GAG crystal, and then there's a 46 keV escape peak that is well separated because we're talking about 17% energy resolution. Now, a real GAG crystal would have about 4.2% energy resolution, but we're reading ours out with 4 silicon PMs on each of the 4 sections of the crystals. We give up a little bit of resolution. We could get that back with eventually more planning and building. We've also done, wrong way. We've also done a study with BA133 source with 4 very close together gamma rays, 276, 302, 356, and 386. Although you can't see them by eye, you can see the shoulders on the sides of them, and then when we reconstruct that in our signal, we could see each one of those identified peaks. So we're quite happy with the detector sensor that we're going to be flying in space for this test. And we have some performance. The 4 crystals have 3 crystals which are pretty fast and lower light yield. We have 1 crystal that's slightly slower and more light yield of the 4. The energy resolution is kind of what we expect with the silicon PM. As you get the higher energy, you go down to about 10%. And it's at the energies that we're expecting to use this at, we're going to be somewhere around the 20% mark. So we're kind of happy with both the linearity and the energy resolution for the actual sensor head that we're going to be flying in this space test. So the actual detector, although it does have this central core GAG crystal with 4 cubes, each one read out by 4 silicon PMs, which are located in this green region, and the readout array. It's going to be surrounded by a Avito ray being built by Elgin, and then right now it's under test at Marshall Space Flight Center. It's being read out with 1 photo tube from Hamamatsu, which is space rated, and we've, on a previous project in my group with Marshall Space Flight Center, this is the exact same photo tube we use for the neutron sensor, which is right now operated in the International Space Station, and is also the one that's going to be going to the moon as well. So we're very confident on that photo sensor, but for the GAG crystal, we wanted to use a silicon PM due to its more robust. And then once that's all assembled, we encase that in a radiation shield, which I'll show more about that in a little while. So here's a depiction of the test that's underway. I told you it was a small detector, 4 cubes of GAGG crystal. Each cube is 24 by 24 by 17 millimeters. A little bit of quartz on the sides and on the readout before you get to the silicon PMs. That has to fit inside this Vito ray cube, which is then a plastic scintillator. This is the top of the plastic scintillator that would go on there, so it'd be completely sealed and encased in the Vito. And we show you the size of it with a cup that's depicted here. And then when you look at shining an americium source on all the different sides of this scintillator, you can see the responses we have for all the different locations that we tried. And so we're fairly happy that our efficiency, because we're only collecting the light from all of this entire Vito array from onto 1 p.m. on the bottom here. And so we wanted to make sure that all the light from the Vito array is making it to the photo sensor, so we know exactly that we're recording enough light to do the Vito. So the concept here of this double delayed coincidence, along with the Vito array, is that we're going to have this neutrino conversion signal. It's going to have some length to it, and then there'll be a second pulse after the conversion electron. There'll be the excited state nuclear decay 66% of the time. That'll give us then a secondary pulse, and if both of these signals don't have a Vito associated with it, it'll be considered a good event, and even our electronics will handle if there's a second pulse in between these two, but it was in coincidence with something in the Vito, that our electronics will know not to use that or consider it. And so that's the technique that we're going to make this clean. Very similar technique to how Cohen and Reines did it with the anti-neutrino detection. And that's, it's a counterintuitive. Why could we go, if you look at the poster, it says topics are large detectors for neutrinos, and we're talking about something fairly small, because we are effectively a large detector, because we're super big when we have that 10,000 times more neutrino flux. And so we just have to build this correctly. So we've also studied, in advance of our test flight, multiple pulses. We have a conversion electron, and then we have a well-defined gamma ray that we expect to see with a delayed pulse. It could be anywhere from half a lifetime out to 10 lifetimes. It could be really close together, and you could have the secondary pulse actually embedded in the tail of the conversion electron signal, or you could have it very well separated. We're trying to understand how to do all of this with our electronics for our test flight. So both figures here demonstrate the double pulse event, well separated or embedded in the tail of the other. And we think we have, with the very good energy resolution that we're going to see, we'll actually be able to use this detector down to about 400 nanoseconds for certainty, maybe even going as low as 100 to 150 nanoseconds for the earliest of the secondary pulse. Simulations, what we've taken is we've taken the galactic cosmic rays that we would expect at solar radius, or due to solar modulation, at 7 solar radii. We've randomly generated all the events that should be occurring at that point, and we then took all the galactic gamma rays and its spectrum, and we rolled all the dices in a Monte Carlo to simulate this, and we've also thrown in there the correct number of neutrinos that we would expect at 7 solar radii. And we reconstruct our 3 different types of events, and we can see we get the half-lives right. But we also know that using the truth table of the Monte Carlo, that 15% of these events are actually fake double coincidences from galactic cosmic rays and galactic gamma rays. But we think 15% is pretty good. There could be some improvements to this with offline analysis. But the one question for the real advancement of this detector as a NASA project is, are the galactic gamma rays related in some way to the galactic cosmic rays? And we can't answer that question. So one of the objectives of the flight test of this detector is going to be, do we see the correct rates based on our random galactic gamma rays and our random galactic cosmic rays, or is there some enhancement due to the fact that one might be correlated to the other? And then, of course, they use 3 different pulses. So we also need this radiation shielding, because there's a lot of low-energy X-rays in space, and that's what the shielding is about. We can't just launch a piece of iron into space, because as a CubeSat, it has no re-entry control, so it has to burn up. So we've chosen to go with an epoxy-based, metal dust-loaded, and we want to shield it from protons and from electrons, and we've chosen a thickness of the shielding that'll help us eliminate some of the backgrounds. So our test detector is going to sit inside a 3U CubeSat One UV CubeSat is 10 centimeters by 10 centimeters by 11 centimeters, and then there's 3 of those, so it's 33 centimeters long. Nanoavionics is providing us the car. The CubeSat's like a car. You buy a car for what you want to do. You put the passenger in it. The passenger is our test detector, and it provides everything. So for $239,000, Nanoavionics is providing us essentially the test car. The CubeSat launch is requested to be either a SpaceX or a Rocket Lab launch. 8 kilogram 3U CubeSat, which is pretty on the heavy side, but it's allowable. And we're asking for a low Earth orbit polar. We're only going to take data when we're over the poles, underneath the hole in the radiation belts. The launch is going to be about $180,000 from Rocket Lab. Of course, they're launching lots of other things with this, not just us. The SCAN, the Space Communications and Networks, is already providing us a grant of $425,000 for 2 years of communications. And our aim is to do a launch in late summer or fall of 2024. And the conclusion of this is that although this is the CubeSat launch and this is testing the concept and getting the data in space, we've already started with a team of engineers who spent 10 weeks working with us to come up with a real understanding of what the cost of 125 kilograms of gallium detector close to the sun at 7 solar radii will be. And after doing a lot of work with this team of engineers, they came up with a price of $326 million to build and to launch this detector. It's going to be a Falcon Heavy launch, which luckily is a little less expensive than a Delta IV Heavy. And it's 5 years of operation. It'll be the solar shield, then a tungsten shield, then 125 kilograms of gallium in a detector of something like GAGG or the new gallium oxide detector, which would be 75% gallium, which is under development at the University of North Carolina. And so the goal here is a future mission. Now, why are we so cheap? We're inexpensive because we're copying everything we could copy from Solar Pro Plus. The heat shield, the solar panels, the radiators, the bus. And what we're just putting into this is the new components. So our hope is a future mission called the Neutrino Solar Orbiting Lab, close to the sun, to demonstrate that we can collect about 400 solar neutrinos in about 5 years of operations. So thank you.
Yeah, thanks a lot for the nice talk. There's room for questions. Oh, many questions. Yeah.
Thank you. What drove you to decision to use a beam team for the video readout? Because it's kind of anisotropic, so on one side it's more efficient than on the other side, so you have an anisotropy in your background which could bias you somehow. Wouldn't it be much easier to have several smaller silicon PMs more uniformly distributed around for the video readout?
We had them. Essentially, we had them. That's why we chose them. We have a huge stack of them from the neutron detector that's in the space station right now, and we have a huge stack of them because we're building the one that's flying on Lunar Gateway into the moon. And so we have a lot of them there, and we were comfortable to continue using them. That was the only reason.
I see. Okay. Okay, thanks.
So what neutrino physics would you address doing this?
There's the decoherent-coherent transition. So 10 MeV neutrinos at 35 solar radii goes from coherent to decoherent transition. And if you could measure, and then of course at 1 MeV neutrinos, that's right at the like 5 solar radius distance. And so if you could map out the transition from coherent to decoherent as a function of energy, then, and this is something that Francis Hausen and I worked on one day at a Hawaii conference. And so I didn't put those plots in this, but after this conference, I'm heading to Krakow for a physics conference where I present this, but I don't present the detector, I present the physics side. And you could see all of the different transitions and going from through that decoherent region. And that's the one thing you could do in space, that you can't take a neutrino detector on Earth and move the Earth in and out of the the coherent, decoherent. And you could actually look at neutrino transport theory, and you can see which one of the 10 are correct because they're wildly varying. But this is the same graph when you take like the Borexino, the snow, the ice cube result, and you see it as a function of energy doing that curve. But this is a different way to approach it, which would be much more accurate and much more illuminating of the particle physics. Now that particle physics doesn't get me approval to do this through NASA. For NASA, I have to do something from heliophysics. And Regina, of course, at Goddard has a lot of knowledge of what they're interested in. And they're more interested in understanding the core of the sun. And so we actually could do nuclear physics, we could do particle physics, and we could address several of the key elements of the heliophysics major goals in the decadal survey.
Thanks. There's room for one question.
So if you expect 400 neutrinos in 5 years in low Earth orbit?
No, not low Earth orbit. This is at 7 solar radii.
So for the present year gadget, you don't expect anything?
Well, there's only one way we'll see neutrinos with the CubeSat, and that is if there's a supernova and all the detectors on Earth measure a bunch of neutrinos and they tell us the time, we can look and see if we see a few of them. And that's the only way we'll ever see a neutrino with the CubeSat. The CubeSat's just going to test the background of the gamma ray, galactic ray correlation, if there's any enhancement to that rate, as well as prove the detector could work in space.
Okay, I just wonder, I mean, all the things which you want to measure are rather well known and have been measured, so what do you really learn? Just that with this exact detector, the rates that are there? Or?
Well, there are things like fluorine and oxygen and nitrogen fusion, which should be expected in the standard solar model, and they're not seen at the correct rate here on Earth. They may be shielded because they're inside the PP fusion, but with a real detector close to the sun, you could go off the ecliptic and look down.
Okay, I understand. No, but with the present demonstrator, you're only looking for the background. But this background should be rather well known from other measurements, so I wonder what you really learn from it.
Well, no, the CubeSat's only going to measure the background, and the background, no one knows if the galactic gamma rays and galactic cosmic rays are correlated, or how well they're correlated. So that's the main proof of principle in the flight test on the very small detector that's going in Earth orbit.
Okay. No, thanks for the question. I propose to continue the discussion after the session eventually. So let's thank the speaker again and move on to the next speaker. So the next speaker is Adriano Di Giovanni, who will talk about the scientific payload of Light 1, a 3U CubeSat mission for the detection of terrestrial gamma ray flashes.
Okay, thank you very much. It's an honor for me to present for the 5th time the Light 1 instrument. This is an Emirati-led space mission that has been developed in the last 3 years by New York University, Abu Dhabi, and other local entities, and of course international entities as JAXA. I'm from Gran Sasso Science Institute, but my former life I used to be the research scientist at U Abu Dhabi. So this detector has been developed in order to study terrestrial gamma ray flashes, and it is currently orbiting in LEO orbit at the same altitude and inclination of the International Space Station. So we'll give you a brief introduction about terrestrial gamma ray flashes, what these things are and how these events can be detected. I will spend a few seconds describing this standard called CubeSat, even though in the previous talk you already grasped most of the details. Then I will go more in detail about the Light 1 mission and its scientific payloads. And I will show the first flight data. When I say first flight data, I mean 1 week old, because we just entered the flight operation. So in case you are looking for something new to do in the next few years, I strongly suggest you to drive your attention to the CubeSat business, because it's something that can give you a lot of opportunities, either in doing some rocket science, but also for testing purposes of your detectors. So terrestrial gamma ray flashes. So we are in the Cold War. There is a high interest in detecting nuclear proliferation in the world. So several satellites were put on orbit in order to detect gamma ray bursts from gamma emission somehow related to nuclear proliferation on Earth. And strange enough, this Vela could detect 16 gamma ray bursts coming from outside, from the universe. And this was kind of unexpected, but ideally was the first evidence of the existence of gamma ray bursts. Then in the 90s, the BATS experiment could detect thousands of these events. But again, something really strange happened because they could detect gamma ray bursts, but also gamma ray bursts coming from ground. And this was expected. I think there is, okay, that should work. So these events were actually characterized by an high influence of gammas in a very short time. And more recently, the Agile satellite and the Fermi satellite could actually detect TGF as side products of their main core science. And actually on the right, you see a typical gamma ray burst terrestrial gamma ray flash detected by Agile, in which you can see that the events last less than 1 millisecond, and the energy spread can be quite diverse. So we go from X-rays to high energy gammas, like 100 MeV gammas. Today we have only one detector that has been tailored around the TGF science, and is called ESIM, that is at the moment, not the moment, it's plugged on the Colombo platform on the International Space Station. Taranis was supposed to start operation in 2020, but unfortunately it was on board the Vega 17 mission that failed the launch, so it never got to orbit. So a few more details about terrestrial gamma ray flashes. So these events are believed to be triggered by lightning or high intensity thunderstorms. The idea is that whenever you have a lightning, you have a strong electric field, and if you have an effective seeding mechanism, so electrons in that region, you can produce gamma via Bremsstrahlung emission. Also, TGFs featured several other counterparties, like electron beams, neutron from photoproduction, and of course radio emission due to the lightning. So the event is, as I said, very short. It's in the order of hundreds of nanoseconds, while the energy range can be quite wide. So we have an estimation from Fermi, and we more or less know that we have like 400,000 events per year on Earth. So there is quite a big sample of TGF that could be achieved by a space mission. The other relevant information that we know is that the most intense thunderstorms on Earth are distributed along the equatorial region. So if we have a satellite that cannot operate 100% duty cycle, at least we know where we should operate the satellite in order to maximize the capability of detecting terrestrial gamma ray flashes. So CubeSat, it's as we saw a few minutes ago, it's a standardized bus This one is basically provided by the nanoavionics. And you are seeing a more or less typical 3U CubeSat in which we have 3 units, and in general about 1.3, 1.4 units are occupied by the subsystem required to operate the satellite. The main characteristics is that okay, constraints are quite relevant. This kind of mission, it's cheap. We were talking about cheap mission, negligible compared to the standard space mission, and they could have little to no propulsion. So basically, you are dealing with free fall objects once put on orbit. So the Light 1 mission has been tailored around these requirements. So we want, first of all, to build an instrument capable of surviving the mechanical stress of a SpaceX launch. We wanted to be on time, so from the PDR to on-orbit operation, it took less than 3 years, and in a COVID time, you can imagine that wasn't a piece of cake achieving these requirements. So we want to measure the particle rate in a particle rate on orbit. We want to measure terrestrial gamma ray flashes at sub-microsecond time scale, and of course we want to space qualify the technology that is on board the satellite. So the orbit is identical to the International Space Station orbit because the satellite was deployed from the ISS. And then also we want to measure the intensity in the South Atlantic anomaly region in which the magnetic field of Earth it's weak, so we can basically be subjected to a very high intensity particle rate, particle fluency. So our detector is actually able to provide detection with a time resolution of 100 nanoseconds, considering all the parameters in the satellite. So our goal is to achieve an absolute timing of about 4 microseconds. That is critical in order to cross-check your observation with TGF observed from other experiments. So we have 2 different payloads that we call PMT and SIPM payload because we are using 2 different technologies for measuring terrestrial gamma ray flashes. In total, we have about 2.1 kilograms of payload. We do everything with less than 6 watts in average, and the data budget is a big constraint because we can stream to ground 50 megabytes per day maximum. So that's the 3D model of the satellite, in which we have the 2 scientific payloads on the left and the right, and in between the required subsystem for operating the mission. So very briefly, so the payload, both payloads are housed inside an aluminum box that is used to physically connect the scientific instrument to the bus of the CubeSat, and this is the 3D model of the inner part of the payload, so the active region. So everything is very compact and small. So we are talking about of a volume that is less than 1 liter. The detector consists of a core instrument. It's a scintillating crystal coupled to an array of photosensors, and we have a VITO system all around to label and tag charged particle-induced events. So the VITO is composed by 8 tiles of plastic scintillator with the wavelength shifter fiber embedded, and 8 silicon photomultiplier developed by Advanced. So we are not measuring charge with the VITO, we only get the digital response. The inner detector is composed of a target, so 4 optically independent crystals read out by as many photosensors. So in one case we have photomultiplier tubes, in the second case, silicon photomultiplier tubes. So that's the kind of photosensors that we decide to use in our mission. So I don't think it's required now to go through all the pros and cons of operating these two different devices. But this will be one of the first missions that could basically qualify two different technology at the same time and the same conditions. So the crystals in the two payloads are very similar to each other. So in one payload we have four cerium bromide low background crystals that you can see in here, and we have a quartz window in order to be able to couple the photosensing devices. In the other payloads, we have two cerium bromide low background crystals and two lanthanum bromochloride crystals. So these two crystals are very similar, are very fast, they have a decent light yield. The main difference is that the cerium bromide is much less, I would say, silent compared to the lanthanum bromochloride, that it's somehow better in the energy resolution. So the proximity electronic, excuse the space jargon, so for normal people is front-end and readout electronics, has been, of course, customized based on the constraints of the mission. Everything has been built using components of the shelf in order to be within the requirements of the budget. And so this is the power supply unit, the electronic, the controller board in which we operate basically all the operation, because we cannot afford to stream to ground all the waveforms, so we need to do a real processing on board. And yes, so that's the picture of the two photosensing arrays. So we have 4 photomultipliers in the PMT array, 4 multipixel photon counters from Hamamatsu in the SIPM payload. So if you remove the outer box, that's what you would see. So the Vito, and inside you have the target, the photomultiplier tubes, the Vito electronics, the power supply units, and the controller board. So the satellite has been launched on December 21st, the day after reached the International Space Station, from where has been deployed on February the 3rd. So it took like 2 months in order to fully commission the bus. And then we started the commissioning phase of the payload that lasted for roughly 1 month. And on May 10th, we started the flight operation. It will be a sad story, because in October, December, so we don't have propulsion, and we are orbiting in a very low orbit. So the satellite will start re-entering the atmosphere and eventually got burned. So this is the first measurement that we did, and it's also used to explain how this CubeSat works. So we can measure rate at this threshold. I'm not able to give you what this threshold corresponds in energy at the moment. We'll be able to do it soon. So the first operation, we power on the payload and measure the pedestals of the electronics. Then there will be a gap in time, and this time is required to put the payload in the flying mode. And then we start collecting the rates. Of course, we cannot operate the detector 100% duty cycle because of power constraints. So from this point to this point is basically 60% of the orbit, and one orbit lasts about 90 minutes. So we keep repeating this game, and then we could actually measure the rate in more or less 1 day of operations. And so these spikes that you could see here is when the satellite was on nearby the South Atlantic anomaly region. So my conclusion, so Light 1 was launched at the end of December using the Space Falcon 9 Dragon rocket. It was set into orbit 2 months later. We completed the LEOP the launch and the early orbit phase, the commissioning of the payload, and now we are in the flight condition. It has been a tremendous opportunity for us to learn, but also to teach students on this project. And now we are starting working on trying to see whether in the first week of operation we detect terrestrial gamma ray flashes. The last thing that I would like to say is that a week ago, more or less, Light 1 was above the Elba Island. So I thought this was nice to show. Thank you very much.
Thanks, Adriano, for this nice overview. It's actually nice to see the whole lifetime of this.
Yeah.
So, questions?
So the segmentation of the crystal, does it give you any rough directionality? And related to this, I noticed that you have a reaction wheel.
Yes.
Is the attitude important to you, or?
Well, it's important for two reasons. One, it's an instrumental reason because we have, so we transmit data in S-band mode. So in our case, the S-band antenna is directional because we want we are constrained by the power. So we use the attitude control to orient the satellite. By design, we asked the nanoavionics to provide a system that, was flying nadir-oriented, even though this is not critical. Not critical. It's so this is, I would say, more a proof of concept than a real science mission. Even though there is, if you look at the simulation, it's possible to detect terrestrial gamma ray flashes, especially if we are able to cross-check existing catalogs. So.
If you keep the same orbit as the ISS, why couldn't you just leave the thing on the ISS and watch from there?
Well, that was my that was our dream, but we couldn't. But actually, that would be the
For political reasons, or why?
Because it's they have to allow you to put stuff on ISS, so it's not. And with the time scale that we had, this was impossible. But I agree that would be something that would also increase the lifetime of the satellite, of the mission.
Space movie is quite easy to do that.
Yeah, exactly.
You have these flywheels for attitude control, but flywheels used to go into saturation once they rotate with the maximum speed, and then you need a propulsion to desaturate them, but you don't have any propulsion. So how you solve this problem?
So we don't solve this problem. We simply switch off the payload during the phase in which we know that the rotating wheels will be operated at the maximum value. And then I think nanoavionics implemented a sort of feedback that try to desaturate and actually this is one of the reasons behind the fact that the LEOP lasted for about 2 months. So they wanted to.
And then just forget about it.
Yeah.
Because you will build up angular momentum,
Exactly,
and at some point it will just spinning forever, right?
Yes,
Yeah.
exactly.
Okay. Thank you.
Oh, yeah, maybe a very quick question there. We move on otherwise.
Again, on attitude control system, do you have a star camera to know where you are pointing at?
Unfortunately, we don't, because for measuring terrestrial gamma ray flashes, we know that the terrestrial gamma ray flashes comes from ground, and we know the timing with a very nice resolution. So we don't know. We don't have a star tracker. So if this is the question, because we think that we could measure terrestrial gamma ray flashes even without. Problem is, so if you want to detect gamma rays and you want to have a nice sample, you need to have a lot of weight. The target should be massive. But again, we also got an exception from JAXA in order to have a slightly larger mass on board. So, but ideally, you're right. So it would be much better to have a star tracker.
Okay, let's thank the speaker again, and we go. Okay, the next speaker is Nicolas Arno. So we switch gear, we go back to ground. And I will talk about LIGO and Virgo detector characterization and data quality, contribution to the O3 run and preparation for the O4 run.
Okay, good afternoon, everybody. So I'm going to talk about gravitational wave detectors, but not directly on the hardware itself, more on the noise that is globally produced and how we deal with it on a daily basis. So I will briefly remind you what our ground-based detectors look like, and then I will focus on the DETCAR activities, so detector characterization and data quality. I will briefly remind you what we have discovered during the last data taking period called O3. Then I will focus on the two main categories of noises that we have, the transient and spectral ones, show you how sensitivity have improved over time, how we validate gravitational wave candidates, and finally conclude on the next data taking period and what will come after that. So our detectors are Michelson interferometers, so you have the laser source, the beam splitter, the two arms with the reflective mirrors at the end, and we detect the interference power at the output. Because gravitational wave will have a differential effect on the optical path in the arms, and so that will change the interference condition, and we will see that as a variation of the detected power. So as you can see, the optical layout is much more complicated than a single Michelson. That's to improve the sensitivity, and that also makes the whole thing more difficult to control. Basically, we are limited by three types of noises. The fundamental ones, for instance, the quantum noises. The environmental noise, although the detector is as shielded as possible from the outside environment, we still see it. But our main kind of noises are the technical noises, those which in principle should not be there, but are there because we have a real apparatus. And so dealing with them is a continuous struggle. So we have groups both in Virgo and LIGO called the DETCHAR, that stands for Detector Characterization and Data Quality, and we really focus on understanding the noises and try to disentangle real events from noise fluctuations. So we have a kind of instrument cycle that is not uncommon. Basically, we do upgrades, then we commission the new detector, we take data, and back to upgrades, and so on and so forth. And at each of these steps, DETCAR activities are very important. We try to track the noise sources in order to improve the sensitivity, which is a very complicated thing depending on frequency. So we usually simplify it by looking at a single number, which is the binary neutron star range. That's basically the distance to which we can detect a binary neutron star system when it merges. So the better the sensitivity, the larger this distance. We also work on improving the stability to make the duty cycle of the instrument larger. We make the data set that people can analyze, and we also focus, as I said, on the individual events to see if they are real or background. And we do that either at the level of a single detector or globally, because the LIGO and Virgo detectors analyze their data together. So this is a sketch from this reference that shows you how all this works. So we start from the interferometers with an S, so really all the data together. We calibrate the raw data to get h of t, the strain channel that could contain gravitational waves. Then we apply those DETCAR methods to check the quality of the data. That goes to all the searches that at the end provide candidates that we have to validate. And if the validation is okay, then it goes to our catalogs and we measure the source parameters. And at all these steps, we need data quality and detector characterization activities. And we also rely a lot on these additional sensors that are here to probe the environment of the detector and to measure what's going on. That helps a lot to separate real signals from background. We do that at very different latencies, from online to months or even years after the data have been taken. And as I said, we do this detector by detector, but also globally at the network level. So our last data taking period was the O3 run. That lasted 6 plus 5, so a total of 11 months. The last month was eaten up by the COVID-19 pandemic, so that was in 2019, 2020. Here you have some ideas of how our detector works in terms of duty cycles. So for each of the 3 detectors, you have the monthly duty cycle, and roughly that's between 70 and 80% for each detector. And at the bottom, you have the combinations when you want to have pairs, or even the 3 detectors running together, so that will be the yellow, the yellow bars. And for the last 5 months of the run, we were able to go above 50%, with 50% of the time the 3 detectors running. If you are interested in our data, you can download them on this GWOSC website, where you can get both individual events and entire runs. So just one word about the O3 results. We got like 79 new signals that added up to the 11 we had before. So we have like now 90 gravitational wave candidates. And what is maybe important is to see how the cumulative number of signals increased with time. And so really that shows that the sensitivity and the duty cycle of the detectors improved. And you can find more about the results in the various links that are here. So now let's move to the noises. So the first category are the transient noises that we call glitch. So that's really a burst of noise with a distinctive time frequency signature. You can see examples here on those spectrograms. So you have time on the x-axis, frequency on the y-axis, and the brighter the color, the stronger the noise is above the floor level. So those glitches have distinct durations, bandwidth, and also signal-to-noise ratios. And they can originate from many things: the hardware, the software, for instance, the control systems. Most of the time, or often enough, they are unknowns. Sometimes there are additional auxiliary channels that witness them and that can help us understand that, yes, that noise occurred. And sometimes the origin is unknown, and we have no real way to find that they are occurring. So they decrease the sensitivity to gravitational waves overall by making more false triggers. They could also hide real signals, and they decrease the stability, the duty cycle. The other category are the spectral noises. So this is excess of noise on long time scale in a given frequency range, and there can be many different types. Either they are very narrow lines or wider bumps. I'll show an example later. And again, they can cover real gravitational wave signals that will be periodic, always coming at the same frequency. One thing that you can also see at the bottom right here is that those lines, they can appear, disappear, change frequency, change intensity over time, so that makes their study quite complicated. So ideally, the way we would be fighting those noises is that we will take a frequency range of interest, look at the dominant noise there, find its origin, fix the cause or mitigate the effect. That will make that dominant noise go down. Then another one will start dominating the sensibility, and we will iterate. That's the ideal scenario. In practice, we rely a lot on those additional channels that I already mentioned. Here you have some glitches that we see in the gravitational wave strain channels, and that in fact are correlated with auxiliary channels that tell us that these are connected to thunderstorms around the sites. So we look at correlations in the time domains between the gravitational wave signal and the auxiliary channels, and we can look also at coherences in the frequency domain. So here are two examples of what we have done. So here on those four graphs, you can see how the noise has been improved around 50 Hertz, which is the main frequency in Italy, so on the Virgo detector. So for each of them, you have in blue the level of noise before the work, and in orange after. And you can see that really we can decrease these big peaks at 50 Hertz and also improve some structures around the 50 Hertz. So that's the kind of thing that we try to do to work on in a given frequency range. Another example is that we, in one of the LIGO detectors, they saw some signals periodic in a magnetometer. They could correlate that with a compressor being on and off, and that was indeed shown to make some glitches in the data. So I mentioned the sensitivity of the detector, so that's something that depends on the frequency, and you can see this characteristic shape with the better sensitivity around 100 or 200 Hertz. And you can see how this has improved for Virgo between 2017 and 2020. So not only the baseline goes down, but you have also less and less structure, which means that we understand this spectral noise and improve it. And again, you can see the same kind of thing, averaging this sensitivity into the single figure of merit I described before, this BNS range, and it's expressed in megaparsec. And you can see for the three detectors over like 3 years how things have improved over time. So as I said, we validate the events. Maybe that will be clearer on that slide. The idea is that we want to make public alerts in low latency, meaning on the order of a few minutes, so that telescopes could point to the source and see if they observe something. So we send alerts through the Gamma Ray Coordination Network, GCN. And the way we do that is that we have a framework called Data Quality Report that is basically a set of automatic checks that run at each interferometer when they are triggered by our database, when a pipeline says, maybe I have a gravitational wave candidate. And within minutes, we get results, and then we can decide if we publish the alert or if we retract it. And we did that about 80 times during the O3 run. So here is a kind of examples to show you that things can be very complicated. You have a spectrogram. It's like 1.5 seconds for one of the LIGO detectors, and you see those kind of things. Then the question is what these things are. And in fact, here you have a characteristic gravitational wave signal. And close to it, you have some feature of a camera shutter. And then you have some glitches due to fast scattering. Scattered light noise is really a big problem for us. These are parasitic beams that are scattering off some moving surface and then recombine to one of our main interferometer beams, creating a lot of pollution. So we are really able to separate the real signal from all these different noises. And if the noise overlaps with the signal, you may remember that this was the case for the famous JW1708-17 event, when we had here the gravitational wave signal and a giant burst in one of the LIGO detectors. We can excise the glitch from the data, and here you have an example. Here you have the spectrogram before and the spectrogram after, and in orange you see that the glitch that has been removed without touching the rest of the data. So we are currently not taking data. We are in an upgrade, moving from this O3 run to the next one, O4, that should hopefully start by the end of the year. It has been delayed, as you may imagine, due to the pandemic in particular. And both LIGO and Virgo are doing significant upgrades with, again, the idea to boost the sensitivity and to make even more detections in the future. So we will be characterizing these new detectors, because each time you have an upgrade, basically you start with a new detector. And one of the things that we do are what we call those noise budgets, where you basically try to sum up all the noise contributions that you know, and that gives you sort of sensitivity that you should get, and you compare it with what you have, that you measure really on the instrument, and then you have to understand the differences. So we'll be focusing on having a larger rate of real signals. So that means we must automate further the systems, reduce the latency, try to look for more things, and in particular, we will be prepared for potential detections of new sources that we haven't seen so far. So as I said, the run should start by the end of the year, and we make periodic updates that you can see here. So basically, we are here. We had the first detections in 01 in 2015. We had this fruitful O3 run in 2019, 2020. And then we plan to run all 2023 for the O4 run, then another period of upgrade and commissioning, and then another run that is called O5. And here you can find the numbers that give you roughly this BNS range that we have done and that we expect for the future. Some references, and just to conclude, if you want to have more concrete hardware, let's say of Virgo, you can look at these two posters from Valerio Boschi and Pietro Chiesa, and they focus on the suspensions, which are a key element of those our detectors. Thank you.
Thanks for these very nice talks. It's nice to see all the hard work at the backstage of these nice observatories. So there is room for questions.
Thanks. I was wondering how much of your noise hunting activity can be transferred to another interferometer. Is it mostly local effects or something that you can export to some other observatory somewhere else, or some observatory of a new generation like Einstein telescope?
I think it's very difficult. There is a part which is lessons learned. When you understand the source of noise, then you can try not to make the same quote-unquote mistake the next time. But if you compare, for instance, the range of the two LIGO detectors, so Hanford in red and Livingstone in blue, they are kind of the same, made by the same people, and you see that there are significant differences in terms of performance. So there are really things that are local. But we use all the experience that we accumulate here, for instance, for Einstein telescope, to try to do some things differently, maybe to do things better, or we learn new noise coupling mechanisms, things that we know that we would have to avoid in the future. But that's very difficult. Yeah, that's what I tried to show you with this never-ending thing, like the same day coming back and again. You have to fight, and then you upgrade, and then you get a new instrument, and you fight again, and so on and so forth. Because you really need to control the detector completely to get the first sensitivity curve, and then to understand what the noises are. It's difficult to do things in between. Until you are controlling your whole detector, then you don't really know what you will get at the end. So it's a surprise each time.
Okay.
Your gravitational wave signal is very specific. So it's this chirp going up with frequency. Whoop. And do you see any noise which can really mimic this? So I remember LIGO had when they found the first signal, they were looking for motorcycles, because a motorcycle can do, it goes up like this. They didn't find any motorcycle. But have you seen any specific thing which really can mimic a signal of the gravitational wave going up in frequency?
We have these glitches that we call the blips, that are, I think, one of the most annoying category, because they really look like chirps. Yeah. From a very high mass thing.
I see.
And those ones, we see them in all three detectors, I think, with different rates, but we see them everywhere, and we have no idea where they are coming from.
Okay.
So they are really polluting your sensitivity, because they will be there, and there may be coincidences, but random coincidences, so they decrease the sensitivity, and so far we have not understood where they were coming from.
So the ultimate trigger will be if you see a signal on several detectors at the same time, then you know it's not a background, right?
That's what we try to do, but with things like that, for instance, you still get coincidences from time to time, and it's
really?
difficult.
Okay.
Yes.
Some aliens, huh? Perfect. Okay, thank you.
Another question. Yeah,
Do you plan to use in O4 techniques such frequency-dependent squeezed light or something like this to reduce especially quantum shot noise?
Yes, we are. I don't remember if I didn't give any details. Maybe I should come closer to see what it says here. But here you see frequency-dependent squeezing. So yes, that's one of the projects that we have both at Virgo and at LIGO. So far at Virgo, the two things, the main interferometer and the frequency-dependent squeezing project, go in parallel. And at some point in the coming weeks, the two will be plugged together, and we will see how that works. But so far, they are proceeding in parallel.
Okay, let's thank the speaker again. We have to move. Okay. Okay, now we go to the last speaker for this, before the poster presentation. So it's Francesco Pandolfi. He will talk about dark PMT, novel directional light dark matter detector based on vertically aligned carbon nanotubes.
Okay, can you hear me now? Yeah? All right. Good afternoon, everybody. I'm going to stand over here because I think it's more natural. I'm Francesco Pandolfi. I'm going to tell you about the dark PMT. So the starting point is this plot. I'm sure many of you are familiar with it. This is the excluded cross-sections of dark matter interaction with normal matter as a function of dark matter mass. And as you know, the high mass region... Hello? Hello? Much better. Yeah. So I was saying, the high mass region here of this plot is populated by all these famous big noble liquid detectors that have done all these nice and stringent limits. But as you can see, as soon as you go below the 1 GeV threshold in mass, you start having extremely weak limits. And actually, this is coincidentally also a region which is predicted by some models, for example, the SIMP model. And the reason behind this is actually quite understandable. All these detectors have been optimized for nuclear recoil, and so they're optimal when the dark matter mass is similar to the nucleus mass. That's when the nuclear recoil is maximum, and so it's easier to see that. But once you go to the light mass regime for dark matter, then you start entering the wall against the ball against wall situation, in which the light dark matter is so light that it will not transfer any recoil to the nucleus, and so you don't see it. So to be fair, when you look for light dark matter, you're not actually interested way too much in nuclear recoil. You're better off if you're looking at electron recoil. So instead of looking at this plot, you should be looking at this other plot. Now there's three key differences in these two plots, actually 3 things I wanted to point out. The first thing is obviously the x-axis range is much different, it's much lighter. The second one is that the y-axis range is also different. It fits between these 2 lines. In general, the limits here are kind of order of 10 to the 6 times weaker than these ones. So this actually means, this is an important point, that in order to be competitive on this plot, you need tons of target, whereas in order to be competitive on this plot, you might get away with just grams of target. And the third thing is that, as you can see, once you go below the about 100 MeV in mass or something, also these limits start becoming much weaker. And this is because all these, most of these detectors are based on ionization signals. And so when you're looking for the ionization signal of these electron recoils, if the recoil becomes too small, then you're going to go below minimum reconstruction thresholds, and you're going to start losing these signals. So the idea that we have is to build a detector based on a solid state target, and in particular a 2-dimensional target, so graphene or nanotubes in particular. The idea is that if you do a back of the envelope calculation, you assume a dark matter wind of light dark matter, so mass between 10 and 100 MeV, and you assume a velocity of 300 kilometers per second, then you have a kinetic energy between 5 and 50 eV, give or take. And that's enough energy to extract an electron from the carbon lattice, because the work function for carbon is 4.7 electron volts, and so you end up with an electron which has a kinetic energy between, say, 1 and 50 electron volts, which is extremely low, and obviously this means that such an electron has extremely short range in matter, so it will be reabsorbed in a normal solid-state target. But the advantage of using a two-dimensional material is that once you extract the electron, you extract it directly into the vacuum. And so it's easier somehow to then make it leave the target without being reabsorbed. So that's the idea we have. And turns out that you can grow nanotubes in the lab. There's this technique called chemical vapor deposition. And since 2020, summer 2020, actually, we installed this new state-of-the-art nanotube growing facility in Rome Sapienza. You can see here how happy we were that we had finally got the chamber, and that's at installation. This is a picture of what we're doing now. These are 4 by 2 centimeter silicon substrates before and after the growth. And you can see that after the growth, they become completely black and opaque because nanotubes happen to absorb light extremely efficiently, visible light. And here you can see a SEM image of a typical growth. This is from a month ago. You can see all the tubes. I hope you can see them at least. There's a lot of, they look like hairs, the parallel tubes, and they're about over 300 microns long. Now the key feature of vertically aligned nanotubes is that they have significantly lower density in the direction of the tubes because the tubes are hollow. And you can see this here. So this is Raman analysis, Raman spectra, on the nanotubes after bombarding them with argon ions in two different directions. So here we bombarded them on the sides of the tubes, and here instead we bombarded them along the tube axes. And you can see that in this case, already at a depth of 15 microns, you recover the pristine nanotube spectrum. So this means that the argon ions have penetrated only up to 10 microns in depth, and then they stopped. Whereas here you can see that the damage is done throughout the whole length of the tubes. In this case, it's 180 microns. So this proves that the density in that direction is much lower. And this actually makes for an ideal solid-state target for dark matter, which would also give you directional sensitivity basically by design, because if you line the tubes in the direction of the wind, then the ejected electrons will be ejected in the direction of the tubes where the density is lower. And so you have a chance of the electron wiggling out of the target, and then you can accelerate it and see it. Whereas if you put it in another direction, the ejected electrons will be reabsorbed and they're lost. So such a target would produce a signal only when it's parallel to the dark matter wind. And so this is the idea. This is the detector concept. We call it a dark PMT. It's similar in concept to a normal PMT. It's just that you have to replace the photocathode with a cathode made of vertically aligned carbon nanotubes. And so this is where the dark matter electron scattering would happen. The electron would be able to leave the forest only if it's in the right direction. And then once it's out, you can accelerate it with an electric field and then smash it into a silicon detector and count it. And so such a detector would have some really attractive features, actually. It would be portable, cheap, and easy to produce. It would be substantially, basically unaffected by thermal noise, again, because the carbon work function is so high. It's almost 5 eV. So you don't need cooling, you don't need cryostats or anything. And as I said, it would have directional sensitivity, which is also a very interesting feature for dark matter searches. And so a search based on these detectors, this is how we envision it. We envision to have 2 arrays, one which is pointing in the direction of Cygnus, so the dark matter wind. And so this array would be sensitive to a dark matter signal. And then another array which is pointing in some other direction and would be dedicated to in situ background measurements. And you can see here, this is the result of a calculation. You can see these are the rates as a function of the recoil energy of the electrons. And this array over here is the black curve, and this other array that's pointing in the wrong direction is the red curve. And so you can see that we do expect a different rate in the 2 detectors. So at least in principle, it should work. And another thing I wanted to show you is that if you focus here, maybe it's not visible, but this axis range goes from 0 to 8 electron volts. And so in principle, such a detector would be sensitive to very low energy electron recoil. So we would be largely much less affected by the electron reconstruction thresholds that I was telling you before that was causing this weakening of the limit at low mass. And so this is why if you do the expected performance of such a detector, you see that we can extend already with only a 1 gram target and only 1 year of 1 gram times 1 year of exposure, we would be able to really extend the low mass region of the sensitivity. So this is basically the Andromeda project. This is how we call it. This is we recently won a PRIN 2020 grant. So it's a 3-year project. It's starting now, literally started last month. It's coordinated by 3 units, INFN, Sapienza, and Roma 3, all based in Rome. And the main objective of the project is to build the first working prototype of a dark PMT. And so, as I showed you, this is how it works. And you can imagine that there's challenges on both sides of the detector. So on one side, you have to identify what the ideal carbon nanotubes are, ideal for this use case, so to be a target for light dark matter. And on the other side, you want to identify what is your optimal your optimal detector to detect KV electrons that are emitted by the cathode. So starting from the nanotubes, we identified 2 crucial aspects that we have to address in order to have an optimal target. The first one is that in chemical vapor deposition, when you grow the tubes, you tend to create a crust layer on the top of the parallel tubes. And the crust layer is not aligned. We call it spaghetti-like, maybe because of an Italian bias. But this crust layer needs to be removed because it would hamper the emission of electrons from the target. And the other aspect that we have identified is that even if the tubes, when you look at them from a distance, from the micron scale, they do look parallel and straight. When you zoom in the nanoscale, you see some wavy structures. And again, also these wavy structures need to be minimized in order to maximize the electron transmission through the tubes. So to address the first issue, the crust, we're working on applying plasma etching to the nanotubes after the growth. So the growth will produce this crust layer, and ideally, if you do etching, what we want to do is just remove the crust without affecting the parallel tubes that are underneath. And so these are really some recent attempts that we've made, basically going from mild etching to more aggressive etching. And you can see already from these SEM images that you have to calibrate this pretty well, because if you go to too aggressive etching, you start damaging the whole tubes, even on the bottom, below the crust, and you don't want that. As for the other problem, the waviness, so we identified some, we have seen, at least in the literature, that the parallelness of the tubes strongly depends on the catalyst seeds that grow the tubes, the iron seeds in our case. And in particular, it's strongly dependent on the density of the seeds, on their uniformity in size, and on the level of oxidation. And so all these 3 aspects will be explored in order to see how to get the most straight tubes as possible. And so right now we're building an evaporation chamber in Rome, so we will do the evaporation and create the seeds ourselves. We will operate in ultra-high vacuum to minimize oxidation as much as we can. And we're aiming for very high seed density and especially very high seed uniformity. And I think this is crucial because it has been shown that seeds with different sizes will grow nanotubes at different rates and at different speeds, basically. And different speeds of growth will naturally lead to these wavy structures, which is what we want to avoid. And that was the nanotube side. Instead, on the other side of the detector, the electron counter for KV electrons, for the benchmark technology that we'll use is APDs, and this is simply because they're simple and cost-effective, and we happen to have some experience with them. But we're keeping as a backup and possible upgrade the use of silicon drift detectors because, this is a proven technology for KV electrons. We know that they work and they have ultimate resolution. And so for these, we're using Hamamatsu APDs, and for these, we have some SDDs that have been produced by FBK, and the electronics has been produced by Politecnico di Milano. And just to give you a snapshot of some of the characterizations that we're doing right now, we have this beautiful electron gun in Roma 3. The electron energy is between 30 and 1,000 electron volts. It's really monochromatic. The energy uncertainty is below 50 milli-electron volts. So it's really, it's really monochromatic. And the current can go as low as a few femtoamps. The beam spot is also small, it's 0.5 millimeters. And what you can see here, this is an example of a characterization of the APD current that the APDs that we've done. This is the current that is created by the APD, the bias current, as a function of the current of the gun which is shooting on it. And you can see that this is for 900 electron volt electrons. You can see that there's a clear correlation, and so this means that the APD is actually seeing these 900 eV electrons. And similar results we've done for 500 and 300, I think, electron volts. And finally, this is a picture of the first, let's call it a prototype. This is the first prototype of the dark PMT that we built in Rome. You can see this is the sketch. You have nanotubes sitting on this side. You have an APD or an SDD sitting on the other side. And you can put a bias between these things. You can also move the distance and put them further away or closer. And this is a picture of it, and it's doing the preliminary measurements in Rome. All right, so this brings me to my conclusions. I hope I convinced you that carbon nanotubes are an exciting new material for light-dark matter searches. And the key element here is that it's a two-dimensional material. So these electrons are ejected directly into the vacuum. And we have this detector concept. We call it dark PMT. It has a lot of nice features. It would be portable and no need of cooling, directional sensitivity. In principle, it should be sensitive to electron recoils of a few electron volts. And so this would be capable of extending the reach of current searches below 40 MeV in mass. Our project is called Andromeda. It's a young and ambitious project that just started in Rome. We aim to build the first dark PMT by the end of, by mid-2025. And by the way, we're hiring, so if you're interested in a postdoc, just hit me up at the coffee break and we can have a chat. Thank you very much.
Yeah, thanks a lot, Francesco. This is very nice detector, very nice idea. So there are questions on the back. I think we have room for more questions.
Hi, thanks for the exciting talk. It's
Where's
very
the question? I
interesting.
can't see it, sorry.
Oh,
there you are.
I was wondering what makes Cygnus your first candidate for pointing your PMTs?
Oh, sorry, I went a little quickly over that. I mean, if our galaxy is immersed in dark matter and dark matter halo, then on Earth there would be an apparent wind of dark matter, and that depends on the direction the solar system is going towards right now, and that happens to be the Cygnus constellation. So if you see a dark matter signal which is compatible with Cygnus, then it's dark matter. If it's coming, I don't know, from the sun, that's probably not dark matter. That's why Cygnus.
One quick question about background.
Mm-hmm.
Did you already try to assess the background expected?
No, I mean, we're not at
Thank
that
you.
level yet. We're at the level of the proof of concept. So we want to demonstrate that this works, and then we're going to have to think about backgrounds. But I mean, of course, this would have to be, I mean, this search that I showed here with the cartoon would obviously have to be done in an underground facility such as Gran Sasso. Then we would have to have shielding and access all of the sources of background. One particular thing that we will have to think about is carbon purity in the nanotubes because of the carbon-14 component. We have ideas on how to minimize that if it is a problem, but we do have a way of measuring it in situ, so we can figure it out.
Yeah, it's actually along the same lines. Any ionization signal will mimic your dark matter, because I don't think you have any way of distinguishing the way the electron was emitted or the energy of the initial electron. So anything that takes out an electron in carbon, you will mimic dark matter. Yeah.
Yes.
So that sounds like scary, but yeah, interesting.
Yeah. I mean, you need obviously all your shielding, all your vetoes, and then hope that you can control the background with the other array.
So you were saying that you need like around a gram of target to achieve kind of competitive limits. How much target mass does one of these PMTs have?
So basically, So once you grow them, as we're growing them right now, not this tall, let's assume 100 microns in length, then 100 microns tubes, forests of 100 microns of height have a mass density of about 1 milligram per square centimeter. So you would need a square meter of target. And you can do that with 100 detectors. We're thinking of 100 detectors with 10 square centimeter, 10 square centimeter photocathode, and that should work.
I have a quick question about the seed layer that you are putting. What kind of material are those?
The what, sorry?
The seeds that you
It's
are
iron.
putting into organic. It's iron?
Iron.
And is the nanotube growing underneath the iron or on top?
The iron stays on the bottom.
Okay.
Yeah.
Interesting. Yeah.
But it's true, there's two different growths. There's two different types. In our case, the iron stays on the bottom, but there's another technique in which the iron goes on the top. Yeah.
Okay. I think we are ready. Thanks again, Francesco. And I think we are ready for the poster review. I give the microphone to Regina that she will take over. And it's a very hard job to present 40 points for this session.
Yeah, I guess we can give.
Oh, you get a new. Oh, sorry.
Okay. No? Okay. Try now. Maybe? Okay. Yeah, I can hear. Perfect. Okay, so so I'm giving the poster review for the detector techniques for cosmology and astroparticle physics session. And really, I just want to encourage everybody to please go check out these posters. There's 42 of them, and so there's no way that I'm going to be able to give them any justice going through them so quickly. But I'm also giving this on behalf of Luciano, who's been doing a great job chairing the session so far. And yeah, let's get started. So there's a lot of topics that are in this session, covering everything from whole detectors and overviews, all the way down to the specific instruments and devices that are reading out the signals. And so we broadly covered them into a few different categories: dark matter, rare events, new physics, neutrino astronomy and neutrino physics, gravitational wave and multi-messenger astrophysics, gamma ray and X-ray telescopes, cosmic rays and antimatter, and then other astrophysics detectors. And this is narrowed down really from, like I said, a very broad set of posters. And so we'll start out, what my approach to this is I'm going to talk a little bit about the themes overall, and then go rather quickly through each of the posters. And so from the dark matter side, there's a lot of discussion not only about WIMPs, which has been a very traditional and well-trodden topic in dark matter, but also going into maybe more novel searches for dark matter, things like dark photons, sterile neutrinos, and these kinds of maybe more emergent dark matter solutions. As far as the rare events go, there's also discussion of like neutrinoless double beta decay, which has been a topic for like a long time, several decades. And then this also covers all different kinds of detection techniques through noble liquids, solid state devices, calorimeters. And so this really covers a very diverse, broad set of topics. And so starting with dark matters and noble liquids, we have the dark side experiment and a neutron veto. We have, this is an imaging detector to use a fast 3D reconstruction. This is complementary to time projection chambers for the noble liquid experiments, like a liquid argon or liquid xenon. There's also a directional dark matter searches. This is the Cygno experiment. And so this is, additional different ways of looking for dark matter, also in the more light dark matter region. This is a TPC prototype for the same experiment. So like I said, there's lots of discussion about the different kinds of detectors and readouts for the broad searches for dark matter. And then this is another detection technique that is using solid state devices that were first explored by the CDMS experiment, and is looking for this is for the sterile neutrinos and other low background rate kind of searches. Continuing on in the dark matter theme, this is another search for dark matter. This is for dark photons. So like I said, expanding beyond the typical WIMP searches. This is a dark matter setup at JLab. And this, like I said, is looking specifically for dark photons, which are heavy partners to, say, a typical photon. This also is looking at a haloscope, again, searching for dark photons. And so this is using kind of a novel dielectric haloscope using a stack of dielectrics, lenses, and photosensors. So this is quite novel searching for dark photons. Moving past dark matter, going into neutrinoless double beta decay, this is the Quarry experiment. And so looking for this lepton flavor violation in the double beta decay experiments. And so these are some physics results, and then a few more about the specific detectors. Going to a liquid argon, the Legend experiment, this is also neutrinoless double beta decay. And so this is just an overview of the whole instrument itself. So we'll continue onward. And then this is looking at low count rates, so for other rare events, using digital silicon photomultipliers as light detectors. And so this is also using liquid noble gases. Continuing on in the rare the rare event experiments, this is a novel high sensitivity analysis looking for trace elements in liquid samples. And so again, trying to push down the backgrounds as low as possible, looking for very, very low sensitivity. Then there is the Icarus experiment, which is also looking for sterile neutrinos, so another kind of dark matter search, using a liquid argon time projection chamber at Fermilab. This is another example of the experiment, the Icarus experiment, looking just further in detail at the system for this instrument. Now, continuing on into other sterile neutrino searches, this is the Tristan detection module. It's a monolithic SSD array, and this is just a goal of looking for sterile neutrinos. Okay, so that was all of the dark matter posters that you can enjoy. Going onward from there, there's neutrino physics and neutrino astronomy. Now, again, there's a lot of outstanding questions in neutrino physics, and it utilizes many different kinds of detector technologies. So there's PMTs, solid-state devices, transition edge sensors, and again, noble liquids. And so this is a common theme throughout this session. So the first one is the neutrino telescope. They have their first results, and it's the largest northern neutrino telescope as of 2022. And so they have some selected results that they are showing in their poster. Now going into the more neutrino physics, this is using the Juno detector near a that is looking also for sterile light neutrinos and also neutrino oscillations. This is near a reactor that uses a large liquid medium to detect these neutrinos. There's also a poster on the Juno collaboration calibration strategy. And so if you want more information, please check out that poster. There's also a few posters on Holmes, which is trying to measure the neutrino mass. And so this is using transition edge sensors in a novel way to try to measure the masses of neutrinos. And then this is the development and commissioning, further details on this experiment. Now going back to kind of the familiar liquid xenon time projection chambers, this is the EXO experiment, and it's looking to explore if neutrinos have a Majorana mass in inverted ordering, so it determines the mass ordering. Yes? Oh, I am sorry, okay. Sorry. Okay. So then continuing forward with other neutrino measurements for neutrino physics, we have the Hyperkamiokande, which is a water Cherenkov detector. And it's also measuring different aspects of neutrino physics and looking for physics beyond the standard model in the neutrino sector. The next poster goes into more detail about the PMT electronic systems for this experiment, for the Hyperkamiokande experiment. And that wraps up the neutrino session. Next, there's gravitational wave and multi-messenger astrophysics. And so there was already a talk in the previous session that kind of gave an overview of the LIGO and Virgo detectors and where they're planning to go. As was advertised in that talk, there are a couple of posters, additionally, that go into detail onto how to reduce the noise further and control systematics for both advanced LIGO and then also the Einstein telescope, which is looking even farther into the future. Additionally, there's more analysis into the two strategies for mitigating these kinds of noise: electrostatic charging and frost formation. And then moving past the gravitational wave detectors into the more electromagnetic side of the multi-messenger astronomy, there are two posters, one on ultra-fast infrared detectors to look for the electromagnetic counterparts to gravitational waves, and then also a poster on the Ultrasat mission, which is a UV telescope that'll launch in 2025 and will have a very wide field of view and look for, observe in the ultraviolet. So now we go to X-ray and gamma ray telescopes. The IXB just launched in December of last year, and so there's quite a few posters, which I would encourage everybody to check out. There's the mission poster that gives an overview of all of the precise polarimetry that will be done. Because, of course, everybody knows that simulations are required to really understand what it is that we're observing with astronomy. There's a poster on IXB OBSIM, which is a simulation framework. And then also there's an analysis of the systematic uncertainties for IXB in the detector response. Finally, we've heard a little bit about Fermi in other talks, but Fermi has been on orbit for 14 years, and this poster shows the performance of the silicon strip tracker after 14 years of operation in space. Okay, so now we go to cosmic rays and antimatter. Now, similarly, there's a few different techniques that we can look, the Cherenkov air showers and magnetic spectrometers specifically, but this also covers a wide variety of detector technologies, such as scintillation detectors, radio antennae, cryogenic magnets, and also solid-state devices, to throw back to a few themes. The first one that I wanted to talk about, or that has a nice poster, is using the IceCube surface array to detect the air showers for cosmic rays. And so this is, IceCube is planning to enhance their cosmic ray capabilities by adding scintillators and radio antenna to the surface of the ice in Antarctica. And there's an additional poster on the scintillation detectors and the DACs for this IceCube surface array. There's also a poster on the Methuselah experiment, which is a detector to study very long-lived particles and cosmic rays, and it uses scintillators and silicon SIPMs. Additionally, there is a poster on the HERD experiment, and this is the goal of this. One of the goals is to measure cosmic rays. It's going to be on the Chinese space station, and this specific poster is on the plastic scintillator detector. There's also additional details on the high-energy cosmic ray detection capabilities on the HERD with the HERD experiment. And so if you're interested in this, I strongly encourage you to check out these couple of posters. And then this is the third one in the series that talks about the detector and the requirements, specifics about the scintillators and the SIPMs that are used, and just more details about the testing. Then beyond that, there's a couple of posters on Minipan And Mini-PAN is designed to look at cosmic ray physics, solar physics, space weather, planetary science. And they have a demonstrator that is a 8 kilogram, 20 watt telescope. And this is, will make a lot of exciting kind of measurements. The second poster talks about the specific detector technologies, the microstrip tracker that's using this framework to analyze the data. Beyond that, there is a poster, or a couple of posters on the Aladino, which is the antimatter large acceptance detector in orbit. And so this is using a superconducting magnetic spectrometer in space. They have a pathfinder planned for the 2030s, and then launching in operations in the mid-2040s. This is an additional poster that goes into more detail about the magnets, the superconducting magnets. And then finally, we have another poster that is broadly speaking on the study of this particular material, this aluminum material, which could be a test bed for high energy physics applications. And so I think that was a very quick summary of the posters, and so I don't want to separate you guys from the coffee too much longer. So I encourage everybody to please check out the poster session during the coffee break.
Just a short announcement, reminder of the program for tonight. At the end of the tonight we have the gala dinner, so at the end of the session, for people staying at other hotels, the buses will bring them to the hotels to change if you want, and then come back here at 8:15. They come back here. We have the gala dinner all together at the Foco di Bosco, and then at the end of the gala dinner, there are buses to go back to the hotels again.